Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to our course on nonlinear control. We are into the final week of this course, and we are going to start off today with the material on finite time stability. So we've already done notions of asymptotic stability, asymptotic convergence, and already seen many methods to actually guarantee asymptotic stability for several nonlinear systems. And we've identified analysis methods and as well as methods for construction of control. So now we are sort of going to look at notions of finite time convergence, because as of until now we have always been focused on convergence that is asymptotic, that is to say in infinite time. However, there is a lot of value and importance to studying finite time convergence as well. One of the reasons obviously is that a lot of real application problems do not obviously have infinite time to perform a specific task. There is a certain fixed amount of time or a finite amount of time, and therefore studying notions of finite time stability makes sense. And it's also known that these kind of finite time convergence controls also help reject disturbance. So this is also something that we will look at to an extent as part of this week's lectures. So starting with finite time stability, this is a notion that was very nicely introduced by a very prominent researcher in India itself, which is Sanjay Bhatt, and I'm glad to say I actually know him very well. And he actually worked during his PhD a long time ago on establishing some very valuable notions of finite time stability. Although there were others before him who did a little bit of work on finite time stability, but the notions were not very properly formalized. And I would say that Sanjay Bhatt can be credited to actually formalizing notions of finite time stability the way we look at it now. So it's that's quite good to know that one of our very own researchers has been the originator of a particular area of control itself. So these are the two references that you see here that we will be using. Both, as you can see, are from Sanjay Bhatt along with his PhD advisor at the time, Dennis Bernstein, who is still an active researcher in Michigan, Ann Arbor. Sanjay Bhatt is of course in India and part of TCS research. So these are the two sort of articles that we are going to focus on to sort of formalize these notions. And these articles are already mentioned here. One is on the Lyapunov analysis of finite time differential equations, and you can see this is in the Proceedings of American Control Conference from 1995. So this is already quite a while ago. And this is the second article is the more formal journal article on and named as Finite Time Stability of Continuous Autonomous Systems. And this was published in the CIAM Journal of Control and Optimization in 2000. So quite old material in some sense. But then this has been the basis of a lot of new developments. All right, it's been the basis of several new developments. So this is what we're going to start talking about today. Yeah, so let's see. Now what is exactly I mean, before we even start talking about finite time stability and so on, we want to understand a few things, understand a few differences as to uh, what we were looking at before, the kind of systems we were looking at before versus the kind of systems we are looking at now. Until now, so I will say until now, always looking at Lipschitz dynamics. What is Lipschitz dynamics? I'm going to sort of write a few things. So we've been looking at, I'm not even going to look at a control system right now. I'm just going to look at a dynamical system and an autonomous nonlinear dynamical system at that, right? So suppose you have a system of the form x dot equals to fx, and suppose this is, I can always have some kind of a neighborhood on which this function is defined. So it maps vectors in Rn to Rn, and then of course we have typical assumptions that f is Lipschitz on in something that we denote as D, and 0, the origin of course contained in D, because we are usually interested in the stability of the origin, right? And there is of course some initial condition, because it is a autonomous system that we are looking at, so there is no explicit time dependence. So it's not of much concern for us to have initial conditions that are non-zero. So 0 initial condition is quite okay, right? So what was this Lipschitz condition, right? So we have not formally looked at this, but basically this condition guarantees, so I will say that this condition guarantees existence of unique solutions. So there are two things, yeah. Here we have existence of a solution and uniqueness of a solution. So there are two things here, okay? So rather important to understand. It's not just one or the other. It says that the solutions exist and as well as they're unique. Yeah. On the other hand, it is well known that if f is C0, which is continuous, then solutions exist and they are not necessarily unique. Okay, so obviously whenever I'm saying something is continuous, something is Lipschitz, I'm always talking about a domain D, right? I mean, it cannot, typically you can't say that the function is, because these are nonlinear functions, so it may not be very nicely behaved everywhere. So I hope one thing is sort of clear, that C0 is a subset of f is Lipschitz implies f is C0. So obviously, because of what we are able to claim from the Lipschitz property is more than what we can claim from the continuity property of the right hand side, you can expect that the requirement of being Lipschitz is something more than continuity. Yeah. So what is this Lipschitz condition, right? So what is this Lipschitz condition? It basically says that there exists some constant, which is the Lipschitz constant, positive, such that norm of fx minus fy is less than equal to L times norm of x minus y for all x and y in this domain D. Okay, so as you can see, this is in fact, looks like a smoothness condition. It looks like a differentiability condition, in fact, right? Because this is how you define differentiability, right? This is how you define differentiability. Because if you look at this carefully, you will see that differentiability at any point x. So if, how would I define say df dx is something like this: limit as h goes to 0, fx plus h minus fx divided by h. All right. So the fact that the norms are bounded like this, and the denominator is obviously x plus h minus x, right? So therefore, I could use this to somehow get a bound on this limit, which means that somehow I can say that the differential exists. So therefore, the Lipschitz condition is a sort of a smoothness condition, and obviously more than continuity. Obviously more than continuity. Okay. So until now, we have always been looking at systems like these, where the right hand sides are Lipschitz. Even though I may not have explicitly stated it everywhere, but we are. And why? Because this guarantees unique existence of unique solutions. Okay. And this is a rather important thing for us. Okay. Now the thing is that we want to switch our focus to something that's a little bit different. And why? Okay, so I'm going to say there is a shift of focus to non-unique solutions. Okay, there's a shift of focus to non-unique solutions. And why? The question would be why? Let's think about this. Suppose I do have finite time convergence. I'm not going to prove anything. I'm just going to argue it. So suppose I have finite time convergence. Typically, what would you expect? That if you remember, even in asymptotic convergence, what do you say? Or asymptotic stability, what do you say? You have stability, obviously, that's one, so I'm not going to go into that. And then you have convergence, right? What does the convergence say? It says that if there exists a delta ball around the origin, from which if you start, all your solutions will converge to the origin. Okay, so all points within the open neighborhood around the origin will converge to the origin. All right, so this is in fact the claim of asymptotic convergence. Now, as you can imagine, a finite time convergence would also have a similar claim, that not just from one point, but from a set of points, say around the origin, you will converge to the origin, right? So what you can say is finite time convergence would imply a set of initial conditions around the origin will converge to it. Important thing is in finite time. This is the important thing. Earlier, everything was happening in infinite time. So actually, it was not. You already understand that the real numbers does not contain infinity. So, but all the convergence was happening as t goes to infinity. T goes to infinity, right? So the convergence was actually until t goes to infinity, you are always very close to the origin, but not actually at the origin. Therefore, it was asymptotic, right? So in the sense that however much you increase time, you actually are never going to reach zero itself. You're always going to reach somewhere very close to zero. Yeah, and depending on where you chose to stop, because humanly impossible to see infinite time, we are fine. I mean, we just go somewhere very close to the origin. But mathematically, you are not at the origin. Okay, and this is a very subtle difference that we need to understand. On the other hand, if you're converging in finite time to the origin, then it is humanly possible, right? Because now you're talking about t going to a real number, a finite real number, and in that finite real time, you will actually go to the origin exactly. You will exactly go to the origin. So now, in some finite real time, from all these different initial conditions, so suppose I make a state space. Yeah, say I make a two-dimensional state space, right? I mean, it's just a phase plane image like we are used to doing. Okay, on this phase plane, right, I may have many different initial conditions. Doing this. Yeah, all these different initial conditions. Yeah, starting from some neighborhood, right? Starting from some neighborhood of the origin, right? Starting from some neighborhood of the origin, actually converge to the origin in finite time. Yeah, so this is a phase plane portrait. I hope you understand that this is a phase plane portrait. All right. So what does it mean now? What does it mean? As I flow forward in time, starting from different initial conditions, I reach the origin. Right? So if I look at these trajectories backward in time, right, I make my time negative time. So t to minus t, I replace t by minus t in this differential equation. Right? Then starting from origin, I have so many different paths I can take. Right? All right. Now this was not possible in the asymptotic case. Why was this not possible in the asymptotic case? Because you in fact never reached the origin at all. You were always very close to the origin. So I mean, it would be, I mean, I would really zoom this in, and then I would still be like, if I did an asymptotic law, I would be something like this, something like this, something really close, but never really going to the origin. Okay. So in the asymptotic case, there was no question of starting from the origin and in backward time going into different trajectories. But here, because I reach the origin in finite time, yeah, in finite time, therefore, I can, if I look at the backward in time trajectories, I have started at the origin and gone to different points, right? This is exactly non-unique trajectories. Yeah, this is exactly non-unique trajectories. What is the meaning of non-unique trajectories? Starting at the same initial condition, I can get multiple trajectories. Okay, so this is, so finite. So what is the point? Finite time convergence definitely leads to non-unique system trajectories in backward time. Okay, in backward time, you're guaranteed to have non-unique trajectories. And the important thing is, this is not allowed by Lipschitz f of x. Okay, if you have a Lipschitz right hand side for the differential equation, then this is not possible. Okay, and therefore our focus is on non-Lipschitz right hand sides. Yeah, but even there it is not too non-Lipschitz. We still don't like to work with functions that have, differential equations which have right hand sides which are completely non-Lipschitz everywhere and all of that. Okay, so we still restrict our attention, at least for this treatment, to very special cases. Yeah? So what is this special cases? So what is our requirement? So that's the important thing we need to sort of characterize and understand carefully as to what is the requirement here. Okay, so this is the system. So what do we require? Informally I will say the requirement. So in fact I will write the differential equation that we are dealing with first, the notation. So y dot of t is f of y of t. So what is it that we require in words, and then we'll formalize it in mathematical terms. Right? We require uniqueness in forward time everywhere but at the origin. Okay, so we will require uniqueness in forward time, A, because the issue was in backward time. That backward time I definitely cannot have uniqueness because I'm looking at finite time convergence, but I can require uniqueness in forward time. So I need to have some kind of Lipschitz property, and I need to I cannot have this property at the origin. Okay, I cannot have this Lipschitzian property at the origin, which is the equilibrium, by the way. So by default all our discussions revolve around the zero equilibrium. Okay, so uniqueness in forward time everywhere but at the origin is what we require, and that's what we formalize. Okay, now what is it? What is the system now? We say that f is again a map from Rn to Rn. C0 in D, which contains the origin, F locally Lipschitz, on D with the origin removed. D with the origin removed, and of course we have f0 equal to 0 to guarantee that origin is in fact an equilibrium. Okay, all right, great. All right, so now without going into too much detail, we already know that solution exists because of continuity of f. Right? So by continuity, which is in the entire domain, solutions do exist. Okay, and further, so this is what I will actually write here. What are the guarantees from the above assumptions? Solutions exist right, for all x in D, that is all initial conditions in D, and further solutions unique for all x0 in Yeah. So this, obviously the existence of solutions for all initial conditions comes from here, and the uniqueness only for D removing the origin comes from here. Okay, right. Great. All right. I hope that's clear. Okay. So now once we have this setup, we are in a good place to define the notion of finite time stability. Okay. What does it say? It says that 0 is finite time stable for 1 if you have a few things, right? If there exists a neighborhood inside our domain D. So again, let me be careful. Zero is contained in both, of course. And there also exists a function which is called the settling time function on this neighborhood. Yeah, such that you have these things happening. A, the settling time function evaluates to 0 if you plug in 0 as the argument. Right? So if the initial condition state is 0, so the way this is stated, that this settling time is a function of initial condition. Okay, so if the initial condition is 0, obviously there is nothing to do, it's an equilibrium, so settling time function is 0, and t x0 goes to 0 as x0 goes to 0, right? So obviously, I mean, it doesn't say it's monotonic or anything, but it says that if your initial conditions are going to 0, then it is but natural to expect that this settling time function also goes to 0. Right? Then B, you have that for all initial conditions in this neighborhood, which with again the origin removed, the solutions, which are denoted say xt0 x0, are unique on this interval. Yeah, are unique. I'll go over this a bit more carefully. Are unique on this interval, right? And further, xt0 x0 is not equal to 0 on times in this interval, but if I take my time going to tx0 exactly, then xt0 x0 is actually 0. Right? What does this statement mean? The statement means that if you have initial conditions which are not at the origin, because we do not have uniqueness from the origin, then these are the solutions. Solutions are depend on the initial time, which is 0, and initial condition, which is x0, right? So if the solutions are unique on 0 tx0, so it's open on the tx0 side, obviously, and they're never 0 here, but as time goes exactly to tx0, then the solution actually goes precisely to 0. Okay, and the last and final one is exactly the Lyapunov stability condition, right? So this is the Lyapunov. This is the same because this has got nothing to do with finite time or infinite time. This is just Lyapunov stability, which says that for all epsilon positive there exists delta positive, such that if your initial conditions begin again in a delta neighborhood of origin, removing the origin, then the solutions remain in an epsilon neighborhood of origin. All right, solutions remain in an epsilon neighborhood of origin. Again, for the same, you use the same time settling time function. Yeah, so the notion of settling time actually justifies its name, right? Because it is exactly the time in which you go to 0, right? And of course there is also a requirement for Lyapunov stability, right? So finite time stability contains the notion of Lyapunov stability as well, right? So and you see the only difference between typical asymptotic stability is two things. One is that t doesn't go to infinity, it just goes to a tx0, it's a settling time function, right? And further, the you are always in each of these parts of this definition, you're always excluding the origin where the solution is not unique, right? So everywhere you see the origin is excluded from the definition. Okay, all right. So and therefore whenever you go to origin also, it is shown in the limit. Okay, because again since you do not have uniqueness from the origin, you cannot really talk about limits and convergence and these notions when you're at the origin. Okay, so that's what's the definition of finite time stability, and we will in fact continue to do more in this direction. Yeah.